Hello viewers, welcome back to this channel. So in this video, I'm going to be handling the final part under structure and bonding, and this is going to be covering explanations involving drawing and naming of shapes of different ions or molecules. So this video is presented to you by Yusuf, and I advise you subscribe to the channel and share the video to your friends so that you can all benefit as a group. So in this video, we are going to be specifically explaining the effect of lone pairs on the molecular geometry of different shapes. And we are going to be saying that the effect of lone pairs on the molecular geometry is going to be explained by Vesper's theory. In the previous video, we are looking at Vesper's theory to be the theory enabling us to draw the shapes and structures of different molecules or ions. So this video is presented to help us and guide us in explaining how the different shapes come about. Like we already talked on about lone pairs of electrons and their effect, the effect between or the repulsion between a lone pair and lone pair, the repulsion between a lone pair and a bond pair, and also the repulsion between two bond pairs. So here we are going to be putting everything in words, and we explain how the different structures can come in existence. So we're going to start with number one, and we're going to say that you explain the structures of the following species. So one is going to be beryllium chloride, the other one is going to be a nitrate ion, the other one is going to be sodium hypochlorite, the other one is or nitrogen hypochlorite, and the other one is going to be chlorate 5 ion, and finally we are going to explain the shape of hydrogen sulfide. So the first molecule, once in the first molecule is going to be barium chloride. Now drawing the structure according to the previous video, structure of barium chloride is going to be in this form. And we are going to explain why this structure is existing in this format. So starting, we are going to say that the explanation for that is going to be barium chloride molecule has two bonding pairs of electrons and it has no lone pairs of electrons. And with that said, the two bonding pairs of electrons that are formed are going to repel each other greatly and equally. When they repel each other greatly and equally, they form a linear molecule with a bond angle of 180 degrees between them. So having no lone pairs of electrons, we only have bond pairs of electrons under the barium chloride molecule. So what these bonding pairs do is that they repel each other greatly and equally, forming a symmetrical molecule which is linear of barium chloride with a bond angle of 180 degrees in between them. That's why barium chloride adopts a linear structure. So such explanations carry a mark. We allocate them marks from 2.5 to 3 marks. And they are very crucial to be knowing them since we are the highly examinable in today's setting. So we are going to go to the nitrate ion, which was our Roman number 2. So during the nitrate ion, remember that it has this negative charge. So the bond that you start with was supposed to be this upper one. And then you are going to be remaining with 2 nitrogen to oxygen bonds, which are going to be the following. So analyzing this one, we are going to say that in the nitrate ion, you change this one, it's not nitrite, it's nitrate. So in the nitrate ion, it possesses 3 bonding pairs of electrons and has no lone pairs of electrons surrounding the central atom, which is nitrogen. And therefore, the 3 bonding pairs of electrons, just like in barium chloride, are going to lie in the same plane and therefore going to repel each other greatly and equally. And once they repel each other greatly and equally, they form what we call a trigonal planar shape with a bond angle of 120 degrees between them. Now, how does 120 come about? 120, since a trigonal shape, trigonal planar is over 360 degrees, and we're having 3 directions that are going to be formed in a trigonal planar. So we divide it by 3 so that we can get 120. So since we have no lone pairs of electrons, we only have bonding pairs of electrons which are going to be 3. The 3 bonding pairs of electrons which lie in the same plane are going to repel each other greatly, and on repelling each other greatly, they end up forming a trigonal planar shape with a bond angle of 120 degrees between them. So that's a brief explanation for all molecules or ions that exist under a trigonal planar shape. Now drawing the structure for nitrile chloride, well, it's going to be in this format. So first we draw the one for chlorine and then we draw the one for oxygen. So you realize that nitrogen has five electron pairs and we only use 3. So we put here 2 of them above. So you're going to say that under the nitrile chloride module, we have 2 bonding pairs of electrons and 1 lone pair of electron. But in the previous video, we said that the 2 bonding pairs of electrons repel each other greatly or equally. But the lone pair to bond pair repulsion, just like in the previous video, we say that its repulsion is always greater. And therefore, this is going to reduce the bond angle, making the whole molecule to become V-shaped, or someone can say to become bent. So, like I said, when you're answering examinations, majority of you mistake V-shape. Instead of writing V-shaped, you write V-shape. Those are different. And if you write V-shape, you're most likely to choose a mark. The structure is called V-shaped, or you can simply say bent. So this is an explanation for any molecule that is going to be for any molecule that is going to be bent. If at all we have one pair of electrons and 2 bonding pairs of electrons. So going to another compound, which is going to be the chloride 5 ion, is going to have this structure. And if you look at this structure, we're having 3 bonding pairs of electrons. In that structure, you're having 3 bonding pairs of electrons together with one lone pair of electrons. So what you're going to say is the chloride 5 ion possesses 3 bonding pairs of electrons and it has only one lone pair of electrons. And you're going to say that the three bonding pairs of electrons are going to repel each other, but the lone pair to bond pair repulsion is going to be greater. And with that being said, this is going to reduce the bond angle, making the whole molecule to become a trigonal pyramidal, to adopt a trigonal pyramidal shape. And that's why the chloride 5 ion is drawn in that format. For as long as it has 3 bonding pairs of electrons and 1 lone pair, or any molecule or any ion which is in that form, the explanation is going to remain the same. So going to hydrogen sulfide, now notice that also hydrogen sulfide, it has a bent shaped structure or a V-shaped structure. So what you're going to say that, we're going to say that the hydrogen sulfide molecule has 2 bonding pairs of electrons that together with 2 lone pairs of electrons. Now we are going to say that since remember that I told you that the repulsion between the lone pair to lone pair is greater than the repulsion between the lone pair to bond pair, and the repulsion between the lone pair to bond pair is greater than the repulsion between the bond pair to bond pairs of electrons. So what we're going to say that here, we are going to say that the repulsion between the 2 lone pairs of electrons is going to be greater than the repulsion between the lone pair and bond pairs of electrons, which is also greater than the repulsion between the bonding pairs of electrons alone. And with that being said, we are going to say that we are going to make a conclusion that this reduces the bond angle to 92 degrees, making the whole molecule V-shaped, or someone can say bent. So when you're drawing your structure, you make sure that you draw your own pairs of electrons alone, and you also draw the bonding pairs alone. But make sure that when you're drawing these bonds, always use a straight line, and the bonds must be touching from the target to the destiny of the atoms that they are going to, or that they are from, for you to earn or to qualify a mark under the shape you have drawn. Now going to the structured questions, you are going to be saying that explain the following. Explain why. Roman number 1, barium bromide has a bond angle of 180 degrees, whereas tin 2 chloride bromide or tin 2 bromide has a bond angle which is less than 120 degrees. So first of all, you have to start by drawing the structure of each. Then when they talk about bond angle, you have to start by drawing the structure of each molecule or compound that is being talked about. And after doing that, we start our explanations. Like I said, we already covered drawing of structures in the second video, and this is the final video which is going to be handling only explanations about the shapes of different molecules. So if you don't watch the second video, make sure that you first check it out before proceeding with this video. So going to this one, you're going to say that barium bromide molecule has 2 bonding pairs of electrons and no lone pair of electrons, and therefore the 2 bonding pairs repel each other greatly and equally, forming a linear molecule. And with that linear molecule, since it's linear, we expect the bond angle to exist between those two atoms of the chloride or the bromide atoms of the bromine atoms to be 180 degrees. But for tin, you're going to say that for tin to bromide molecule, it has two bonding pairs of electrons and one lone pair of electrons. But we say that the two bonding pairs of electrons repel each other, but the repulsion between the lone pair to bond pair is going to be greater. And therefore, this reduces the bond angle, making the whole molecule to become V-shaped, or someone can say bent. So look at Roman number 2, explaining Roman number 2, the sulfate ion is tetrahedral, but the sulfite ion is trigonal pyramidal. So we start by drawing the respective structures of each. So this is the structure for sulfate ion, and this is the structure for a sulfite ion. So under these structures, you can see that this one does not have any lone pairs of electrons, and it has 4 bonding pairs of electrons. By this one, the sulfite, it has 1 lone pair of electrons and it has 3 bonding pairs of electrons. So you're going to be explaining according to what you're saying. That's why it's very crucial for you to start by drawing the structures so that you can see what you're going to put into words or what you're going to be explaining. So you're going to start by saying that the sulfate ion has 4 bonding pairs of electrons, just like we have recognized, without any lone pairs of electrons. So by that, we're going to say that the 4 bonding pairs of electrons are going to partially repel each other or symmetrically repel each other, resulting into a bond angle of 109.28, making the whole molecule to become tetrahedral. But the sulfite ion is we have seen that it has only 3 bonding pairs of electrons and with 1 lone pair of electron. And with that, you're going to say that the 3 bonding pairs of electrons are going to repel each other, but the lone pair to bond pair repulsion is going to be greater. And with that, you're going to say that this is going to reduce the bond angle in the sulfite ion, making the whole molecule to become trigonal pyramidal. Now looking at explanation number 3, sulfur dioxide has a bond angle of 120 degrees, while sulfur dichloride has a bond angle of 109 degrees, although both molecules are V-shaped. So we start by drawing their respective structure. For the structure for sulfur dioxide is as follows, and the structure for sulfur dichloride is as follows. If you analyze the two structures, you see that here we are having only 1 lone pair of electron, and therefore the repulsions that we have in this molecule is going to be the lone pair to bond pair repulsion and also the bond pair to bond pair repulsion only. But in the sulfur dichloride, we are having 2 lone pairs of electrons. That means that we are going to have 3 types of repulsion. We are going to have the lone pair to lone pair repulsion, which is the strongest. We also have the lone pair to bond pair repulsion, which is the second strongest. We also have the bond pair to bond pair repulsion, which is the least strongest. So starting your explanation, you're going to say that the sulfur dioxide molecule has 2 bonding pairs and 1 lone pair of electrons. The 2 bonding pairs of electrons repel each other, but the lone pair to bond pair repulsion is going to be greater, just like earlier said. And with that, you are going to say that this is going to make the bond angle to become 120 degrees. But in the sulfur dichloride molecule, we have seen that it has 2 bonding pairs of electrons, but as well it has 2 lone pairs of electrons. And with that, you are going to say that since the sulfur dichloride molecule has more lone pairs than the sulfur dioxide molecule, there is going to exist a lone pair to lone pair repulsion, and then a lone pair to bond pair repulsion, which is also greater than in sulfur dioxide. And with a combination of all those repulsion, we are going to say that this is going to reduce the bond angle in the sulfur dichloride. Now, when you're presenting these explanations in your questions or in your examinations, what you have to present are the marking points. That's why I bold these words that are required for you to be marked. Marking points must be containing those words. You must acknowledge all the bonds, all the types of bond repulsions that you're having in such a structure or in such a molecule. Now continuing, we are going to be looking at the effect of electronegativity on the size of the bond angles. Now you're going to be seeing that for two molecules or ions in which the central atoms are going to be different, but the bonded atoms are going to be the same, the increase in electronegativity is going to increase attraction for the bonding electrons towards those central atoms. And once that happens, it's going to make the bonding pairs of electrons to become closer to each other. And the more they become closer to each other, the more they become closer to the more electronegative atom than the less electronegative element, the more the electron density around the central atom increases, and this increases repulsion between the different bonding pairs, which causes them to increase in the bond angle. So we are going to be looking at that in details. This is just a simple explanation of what I was talking about. So this implies that the bonding pairs of electrons are closer to the central atom, increasing repulsion between them, which increases the bond angle. So we are going to see that if at all we are having two molecules. Now these two molecules are going to be having the same, for example, if you're having nitrogen oxide, and you're having also water, for instance, if you're to assume that both of these two are going to contain a bend-shaped structure, here the central atom is going to be nitrogen, and here the central atom is going to be oxygen. So on these two, we compare the electronegativities of these central atoms. Now the one which is more electronegative than the other is going to attract, let me say that these are going to be the bonds. The one which is more electronegative of the central atoms, the one which is more electronegative, is going to attract the bonding electrons towards itself, which increases electron density towards it, increasing the bond angle between its molecules or the atoms, which eventually leads to an increased repulsion between the bonding pairs. And in turn, that's where the bond angle is going to be varying from, and you're going to be looking or diving deeper into such explanations. So for now, we are going to say that for two molecules or ions in which the central atoms are similar but the bonded atoms are going to be different, then increased electronegativity of the bonded atoms is going to increase the attraction for bonding electrons by the bonded atoms. Now when that happens, we are removing bonding electrons towards the central atom, and we are pulling them to the bonded atoms. And for that one, since we are removing bonding electrons towards from the central atoms to the bonded atoms, we shall be reducing the bond angle, since we shall be decreasing the electron density, which will in turn reduce the repulsion between the bonding pairs. So we are going to say that by doing so, this makes the bonding pairs of electrons closer to the more electronegative atom, which is bonded, than the less electronegative atom, which is going to be our central atom. Now this means that the bonding pairs of electrons are far apart, leading to a decrease in the repulsion, which further or later reduces the bond angle between the bond pairs. Now diving into the examples under that, we are going to be explaining the following. So Roman number 1, you're going to be explaining why the bond angle in ammonia is 107 while that in phosphine is 94 degrees. Now if you look at such questions, when you do the structures first, you always notice that they all have the same structures. Like here, ammonia is having trigonal pyramidal structure, and also phosphine is having a trigonal pyramidal structure. But in phosphine, the bond angle is 94. In ammonia, the bond angle is 107. And they say that when you're explaining that is because of the difference in electronegativities of the central atoms. So let's look at the elaborative explanation. So in the explanation, you're going to be saying that both ammonia and phosphine molecules adopt a trigonal pyramidal shape. However, the nitrogen atom is going to be more electronegative than the phosphorus atom. And since it's more electronegative than the phosphorus atom, the bonding pairs of electrons are closer to the nitrogen atom in ammonia than they are to the phosphorus atom in phosphine. Now with that being said, we are going to say that this is going to cause an increased repulsion between the bonded pairs of electrons in ammonia molecule than it is in phosphine molecule, and therefore ammonia is going to adopt a bigger bond angle as compared to phosphine. So the takeaway here is that the more electronegative the central atom is, the more closer it attracts the bonding electrons towards itself. And the more it attracts the bonding electrons towards itself, they increase the electron density between the bonding pairs, and hence they increase the repulsion. And once repulsion increases, the bond angle also increases. So nitrogen is more electronegative than phosphorus. That's why for it adopts a larger bond angle in its molecule as compared to phosphorus in phosphine. So explain number 2, which is going to be explain why the bond angle in hydrogen sulfide is 92 while that in water is 105. So if you look here, hydrogen sulfide and water, they all adopt a bend-shaped structure or a V-shaped structure. I said that it's not called a V-shape, it's called a V-shaped structure. So hydrogen sulfide, both of them have the same structures, but in sulfur we're having a bond angle of 92, whereas in oxygen we're having a bond angle of 105 degrees. So let's look at the explanation under that. So with that, we are going to say that both hydrogen sulfide and water molecules adopt the same structure, which is V-shaped structure. That's the first statement. You have to acknowledge the structure that each of them adopts. So we're going to say that, however, the oxygen atom in water is more electronegative than the sulfur atom in hydrogen sulfide. And with that being said, we are going to say that the bonding pairs of electrons are closer to the oxygen atom in water than they are to the sulfur atom in hydrogen sulfide. And we say that with that, this is going to cause an increased repulsion. The increased repulsion comes about by increasing the electron density between the electrons that are being pulled closer to the more electronegative atom. So that increases repulsion between the bonded pairs of electrons in water than it is in hydrogen sulfide. And with that, we say that, therefore, the water molecule has a bigger bond angle than the hydrogen sulfide. So going to explanation number 3, we're going to say that the bond angle in phosphorus trifluoride is 96, while that of phosphorus trifluoride is 96, while that in phosphorus trichloride is 100 degrees. So here you can see that the central atoms are the same, but what has varied is the atoms that are being bonded to. So still here we look at the same issue. We look at electronegativity on fluorine and chlorine, which is more electronegative than the other. And you see that fluorine is more electronegative than the other. Now if it's the other way, that means that, so let's look at, like I explained, if it's the other way, if at all, now here bonding electrons are going to be attracted towards the bonded atoms. And once bonding electrons are attracted towards the bonded atoms, the more, that is reducing bond angle, because the electron density around the central atom is going to be reduced, and hence the repulsion is going to be less. So let's look at the elaborative explanation to put that in words. So you're going to say that both phosphorus trifluoride and phosphorus trichloride molecules adopt a trigonal pyramidal shape. Just like we say that, we start by acknowledging the structure. And then you go to that. However, the fluorine atom is going to be more electronegative than the chlorine atom. And hence the fluorine atoms, therefore, withdraw away the bonded pairs of electrons away from the central atoms, which is away from the phosphorus atom, more than the chlorine atoms do. And therefore, the bonded pairs tend to be far apart in phosphorus trifluoride than they are in phosphorus trichloride, reducing the repulsion between them. And therefore, phosphorus trifluoride has a smaller bond angle as compared to that in phosphorus trichloride. I hope you're understanding these statements. The more the bonded atoms are pulling away electrons to the other, they reduce the electron density around the central atom. And once the electron density is reduced around the central atom, repulsion reduces. Once repulsion reduces, it causes a bond angle which is smaller as compared to the chlorine atom here. Also it pulls out bonding electrons, but it does not do it as fluorine does it. So you find that this one, the bond angle is going to be slightly greater, because there is a greater or high electron density around the central atom, like it is in the phosphorus atom, which is bonded to fluorine atoms. So the explanation is as simple and detailed as that. Now let's look at the other examples. Now looking at another concept, you're going to be looking at the concept of polarity under molecules. Now we had already explained this, or I had already talked about this in the previous video. So you're just going to be talking about it in details. So you're going to say that polarity is a condition of a molecule to have both positive and negative charges. And therefore, polarity of molecules is going to be related to the electronegativity difference between the two atoms that are in a bonding situation, provided they are bonding symmetrically. So we're going to first look at the factors that determine the polarity of the different molecules. And one is going to be the electronegativity difference of the atoms that are present in a given molecule. And the other one is going to be the bond symmetry or the spatial arrangement of the various bonds in the molecule. So here we're going to be saying that polar covalent bonds are going to be formed as a result of difference in electronegativity of the bonding atoms. For example, if you're having hydrogen chloride, like the examples that I gave about polarity, especially when you're explaining acid strength, are going to be halides of group 7 elements. Hydrogen chloride, hydrogen bromide, hydrogen iodide together with the chlorine to chlorine bonds. Most of the covalent molecules. So we're going to say that all molecules in which the atoms are symmetrically distributed around the central atom are going to be nonpolar. This is only possible if the symmetrical distribution of atoms around the central atom are going to be the same, and these are going to be including the following. So the molecules under which polarity is going to be seen, we are going to have the linear molecules, the trigonal planar molecules, the square planar molecules, the triangular molecules, the trigonal bipyramidal molecule, together with the octahedral molecules. And we looked at this more in details in the second video. So we're going to be explaining why carbon tetrachloride is nonpolar, yet the carbon to chlorine bonds in which are present in carbon tetrachlorides are polar. Now here also, when you're explaining these components, you are supposed to first draw the structures. But here I think I left it out by typing errors. So I'm going to say that chlorine is a more electronegative element or atom than carbon, and therefore the chlorine atom tends to attract the bonding electrons towards itself. Now, by doing so, it is going to acquire a partial negative charge, and the carbon atom is going to gain a partial positive charge. Now, this makes the carbon to chlorine bond polar. By partial negative and partial positive, I hope your teacher explained to you this in details and organic chemistry. But however, the whole molecule is going to be nonpolar because it has a tetrahedral structure in which the chlorine atoms are going to be symmetrically distributed above the carbon atom. And in that, you are going to say that this creates equal and opposite dipole moments in all directions that cancel out, making the resultant dipole moment to be equal to 0. So the tetrahedral structure, you'll find that the chlorine atoms are going to be symmetrically arranged around this carbon atom. Now this creates equal but opposite dipole moments in all directions, which cancel out each other, making the resultant dipole moment to be 0. And this makes the whole molecule non-polar. So that's the reason why the carbon to chlorine bond is polar, but the whole molecule of carbon to carbon tetrachloride is non-polar. So part B is going to be the carbon. You are going to explain why the carbon to oxygen bond is polar, but the whole molecule of carbon dioxide is non-polar. So it's going to be the same explanation. We are going to say that oxygen is more electronegative than the carbon atom, and therefore the oxygen atom tends to attract the bonding electrons more towards itself, and by doing so it's going to be acquiring a partial negative charge. And the carbon atom on the other side is going to acquire a partial positive charge. And once they do so, once one atom has a partial negative and the other atom has a partial positive charge, we say that this is going to make the whole carbon to oxygen bond to become polar. However, the whole molecule is going to be non-polar because it has a linear structure in which the oxygen atoms are symmetrically distributed around the carbon atom. Now this creates equal but opposite. This is very important when explaining non-polar molecules. It creates equal but opposite dipole moments in all directions, which cancel out each other, making the resultant dipole moment to be zero. And that's why the whole molecule of carbon dioxide is nonpolar. So we're going to conclude by saying that molecules in which the bonded atoms are not symmetrically distributed around the central atoms, like chloromethane, dichloromethane, trichloromethane, water, and ammonia, are going to have an overall dipole moment over the molecule, and therefore both the individual bonds and the whole molecule are going to be polar. So we are going to finalize our video, or we are going to finalize structure and bonding by the following table, and you call it a topic: the differences between the polar and non-polar molecules. So for the polar molecules, they're going to be asymmetrical, but the non-polar molecules are always going to be symmetrical. And then one end of the molecule is going to be positive, whereas the other end is going to be has another positive, whereas these ones, they do not have distribution of charges at positive or at the opposite ends. And then we are going to look at the interaction through hydrogen bonds, and here we are going to look at the interactions mainly via van der Waals forces of attraction. And then these ones, the polar molecules are always going to have a dipole moment, but the non-polar molecules always lack what you call a dipole moment. So that's it for this video. You're advised to subscribe to the channel and share the video to your friends. We shall meet in the second on another topic.